All right, so we'll go from tiny replacements to GHC to the depths of GHC. Jaro will tell us about higher order patterns for rewrite rules.
Okay, it works. Hello, everyone. I'm Jaro Reinders. I'm from the TU Delft, and I'll tell you a bit about the work I did on implementing higher order patterns for rewrite rules. So I start off with a quick slide in JavaScript. So even if there's people who are not familiar with Haskell, they should be able to follow along. Maybe they're watching this online. So this also shows that the problem is not a Haskell problem, but a programming problem in general. So the programs that you see here are computing the sums of the squares of the first 6 natural numbers. And on top you see an implementation that's completely written as a manual loop. And on the bottom you see an implementation that uses lists and list combinators. So we as functional programmers, I think most of us agree that this second implementation is what how we would want to write our code. But there is a problem with this, and that is that now we're mentioning explicitly that we're using a list or an array, and we're mapping over it and thus creating another list. So we're doing a lot of allocations here that are completely absent in the example at the top. So rewrite rules are one of the approaches that GHC, the Haskell compiler, uses to rewrite programs that are written in the second style to be as efficient as manual loops. So we can continue writing our programs using combinators nicely. So in this talk, I'll tell you a bit about what rewrite rules are and how the matching, GHC does the matching. I'll tell you where it falls short and how my higher order patterns can solve at least one issue remaining with the rewrite rules. And then I'll show the main application, which is to stream fusion, which is one of the optimizations that can do this transformation that I mentioned on the previous slide. And finally, I'll show you how I evaluated this approach and tell you about my conclusions. So, rewrite rules. Rewrite rules were at least described by Sam Payne-Jones and others in a 2001 paper, and they allow you to, as a Haskell user, write your own user-defined optimizations. So how do you do that? You use this special comment syntax with the curly brace dash hash sign, and then you write rules, and then on the following lines you can write a bunch of rules. Each rule starts with a name, in this case map fusion, and then you have this for all with a list of variables, and these are called template variables. I'll explain what they do in a minute. Then there's the main rule that you write. So you write it as an equation, but it's really meant to be read from left to right. So on the left-hand side, you can see that I've written map f applied to map g applied to the list axis. This is called the template, and that's what GHC will search for in your programs. And on the right-hand side, you can see that there's a map of f composed with g applied to axis, and this is well, I'll just call it the right-hand side, and that is what the rewrite rule will rewrite your code into if it finds any occurrences of this template in your code. And so the template variables, fg and axis, can stand for any possible expressions. So this doesn't match the particular code map f, map g, axis, but it maps any occurrence of 2 maps in a row. So the most notable application of this, I think, is in shortcut fusion, as described by Gill et al. In '93. And I think this is actually one of the original motivations for implementing rewrite rules in the first place. It also precedes the general descriptions of rewrite rules, but I wasn't around at the time, so maybe other people can tell you more about this. Okay, so how can the compiler match these rewrite rules? Here I've written example judgments which asserts that the template that we saw on the previous slide matches with this example expression that might occur in your program. So how do we match this? Well, we look at the abstract syntax tree and we decompose it on both sides. So for example, the first step we can take is to use what I've called the application rule. And we can see that on the bottom, there's this application of map f to map g x's. And on the right-hand side, there's this application of map times 2 to map plus 1 y's. This application we can deconstruct and just match both sides separately. And then, so we can continue with this. So on the left-hand side, this map f, map times 2 is also an application again. And then we just have map matching with map, which is a simple variable rule, and the template variable f matching with times 2, which I've called the template variable rule, which basically says that template variables are allowed to match with anything. We can continue this derivation on the right-hand side and see that we can, in fact, complete the whole derivation. And so this template matches this expression. Now, by reading off the assignments, we can see in all the template variable rules, we can actually perform the rewrite, substitute the expression in the proper places in the right-hand side of the rewrite rule, and end up with this single map over our list-wise, and thus we have eliminated one intermediate data structure. Here I'm showing a basic list of all the matching rules. I'm using the names U and V for variables and X, Y, Z, F, G for expressions. And so the reason that there are not so many rules here, while Haskell is quite a big language, is that these rewrite rules actually are only applied on core. So that's after Haskell has been desugared into a small language. So these rules actually cover quite a large part of Haskell already. So let's start looking at the left-hand side. We see here three more structural rules, which just follow the abstract syntax. So for applications, for variables, and for lambdas. Lambdas are a bit special because we want to make sure that we match through alpha equivalence. So even if a variable changes names, we still want to match lambdas. Then here on the bottom right, we have a let float rule, which says that if we have some template and we try to match this to a let, but the template may not start with a let, we can still continue matching the template with the body of the let. But then we need to float out the let, and for that we add an extra side condition which says that the local variables that occur inside the bound expression, there must be no free local variables in that expression. And I'll explain that also in a minute. In the middle on the right is the unfolding rule. So we might be matching and in our program see a variable, but we still have some larger template that we want to match, which is not just a variable. Then we can look at the unfolding, so at the definition of this variable, if it is available, and we can continue matching on that unfolding. And finally, I think the most interesting rule for this presentation is the template variable rule, which states that if we have a template variable in the template, then we can match it against anything. But again, there's this side condition that the free local variables of this expression we're matching against must be, there must be no free local variables in that expression. And why is that? So here I have an example rewrite rule that has one template variable, and it tries to find the function foo applied to a lambda, where the t is in the body of the lambda, and then it rewrites this into just a t. And now if this x that we bind here in the lambda occurs inside this t, then when we rewrite it, it would be outside of its binder, because on the right-hand side of this rewrite rule, there is no lambda, we don't bind x. So that's why GHC has always conservatively required that there's no variables in this in these template variables. So to give a more complete example, there's this this rewrite rule which matches on occurrences of applications of unzip to the function map, which produces a list of tuples. We might want to rewrite that to a tuple of two separate applications of map. Whether or not this is actually increasing performance does not matter for now. Yeah, so we might try to match that against an expression I show here at the bottom. So here I've shown the same left arrow notation. So this on the right hand side is an expression that might occur in your program. And I've lined them up nicely so we don't need to go through the whole derivation tree. I hope you can all visually see which parts need to be matched up. And that is indeed the template variable A should be matched to x minus 1, B to x plus 1, and x's to y's. But now, so we get to these two, we want to make this template variable match with this expression and B match with x plus 1, but that cannot happen because both the targets mention x, which is a local variable. So to solve this problem, my idea was that we need to somehow annotate these template variables with which local variables are they allowed to match on, and keep, yeah. So the approach I've chosen is to change these template variables A and B to instead become functions, f and g, and we can now apply the functions to the local variables that we want to allow them to match on. So in this case, we want to allow both parts of the tuple to use the local variable x. Yeah, we can look at this exact same matching, and now we get two matchings, fx to x minus 1 and gx to x plus 1. And for this, we still don't have a rule, but we can, of course, introduce our own rule, which I've called the higher order pattern rule. And, well, the actual extension is quite straightforward. We add a rule for when a template variable is applied to a list of one or more local variables. So all these variables v need to be local and they need to be distinct for mainly technical reasons, just to for simplicity. But now the main benefit we get out of this is that we can say the free local variables of the expression we match on does not have to be empty. It can be a subset of the local variables that we applied to the template variable. So using this rule, we can finally match our previous two examples, but we haven't seen an actual, so what is an actual real world example of when we would want to use this? And that's where stream fusion comes in. It was originally described by Duncan Coutts in 2007, and it has an advantage over Gill et al.'s original fusion system from '93, in that it's, so one of the main advantages is that it can fuse functions which takes multiple lists as arguments, like the zip function. So it's slightly more powerful in this respect. So what's the main issue with fusion in the first place? Well, why do we want fusion is because if we have these functions like map, which are recursive functions and they are applied in sequence, then the fact that they are recursive means that GHC can do much less optimizations on it. So usually GHC does optimizations, and in particular inlining of functions is a very important optimization GHC can perform. But with recursive function, that is not possible. So lots of GHC standard optimizations don't apply in the case where you have recursive functions. The approach stream fusion takes to solve this is to, instead of using the recursive list data type, we instead use some kind of blueprint for a list. And so we call these blueprints streams. And a stream is just a stepping function and an initial state. And to produce a stream from this to produce a list from this representation, we start with the initial state, we feed it to the stepper function, and we either get to know that the list is ending at this point, or we get one element of the list and we get a next state to which we can repeat this process. Now, the nice thing about these blueprints is that you can write them completely in terms of non-recursive functions, and you can even write combinators on these streams that use no recursion. So for example, this map function applies a function from A to B to streams of A to produce streams of B's. And for that, it just decomposes the streams and changes the step function slightly. The initial state remains the same. And the step function, the only change we make is if it returns an element, then we apply the function that we want to map over our list to this element that our stream produces. So this function is completely non-recursive if you use them multiple times in a row on the same, in a pipeline on a stream, then GHC will just happily inline them and optimize everything away. So that's very nice. But there is a remaining problem with stream fusion, and that is also identified by Duncan Coutts in his paper. It is not easy to fuse occurrences of the concatMap combinator using this approach. So concatMap is a function that takes an outer stream which produces A's, and then for each of these A's produces an inner stream, and it will concatenate all these inner streams together. In general, it's not possible to fuse concatMap, essentially due to this opaque function that requires us to put the inner stream inside the state of the resulting stream, and that just also inhibits GHC standard optimizations. But luckily, it's often used in a limited form, which is fusible. And this limited form can be described by this concatMap S prime function, where we see that we have essentially the stepper function and the initial state directly available as arguments to this function. So the exact details on why this is better can be found in the paper. But for now, just assume this is possible to optimize. So if we want to optimize concatMap to this optimized form, then we can use a rewrite rule. But the rewrite rule that we're using here now has to, again, deal with these local variables which might occur inside the stepper function or inside the initial state of the inner stream. And Duncan Coutts basically said, well, GHC's rewrite rule system is not powerful enough to support rules like this. But so now with higher order patterns, we can finally write this rule and have it work. To evaluate my system, I first of all needed to make a slightly an additional small change to the matching rules of the rewrite rule engine, which has to do with floating lets in cases. I mentioned in the beginning that we can float out lets if they don't mention any local variables, but in fact, in some cases, they do mention local variables, and then we can instead float them inwards. That might duplicate work, but it's often worth it. And it was needed to make this fusion work. I'm still not sure if this is the approach I want to take, or if there are some alternative approaches. So this still needs to be figured out if we actually want this in GHC. So with this extra change, the neo higher order pattern rule for stream fusion can be applied to examples from literature, which works, but of course the real test is to implement a stream fusion framework in GHC, and that's what I did, at least a basic version, so replacing GHC's existing fusion mechanism with a new stream fusion mechanism, and I've evaluated this new implementation on GHC's standard no fifth benchmark suite introduced by Partain, I hope I pronounce his name correctly, in '92. And of course, this has evolved over time. Now, the results show that higher order patterns on my Stream Fusion framework, the new additional concatMap rule, improves performance by 7.6% in running time and 18% allocations. So that's very nice. However, if we compare this new Stream Fusion system, even with the high order pattern rules, to the existing Fusion system, unfortunately, it's not quite competitive, showing an increase in running time of 8% and 30% extra allocations. So, in conclusion, higher order patterns make GHC's rewrite rule mechanism more powerful. You can use it to improve the performance of a Stream Fusion framework. It needs some more work to be practical, but it's promising. And in the paper you can find another use case, which is about rolling back failed fusion. And finally, I want to make a small remark, which is that these benchmarks are really sensitive to GHC's heuristics about inlining. So whenever maybe you improve something in a small part of your program, and then it causes some other thing to not be inlined, which prevents more important optimization. So that's really annoying. So if you've ever played around with rewrite rules and noticed that you couldn't express what you wanted due to these local variables and the rewrite rules not matching, then I encourage you to try GHC 9.8 or later and see if these new higher order patterns can solve your problems. Thank you.
Hi, so in your slide where you first introduced the need for the higher, with the unzip one.
Yeah. Okay.
Right, so let's say if the right-hand side didn't mention X, would your higher order rewrite, so if A and B did not mention X and the actual results were basically, well, they were constant functions, would your higher order rewrite rule then not match, and you'd basically have to add two rewrite rules to deal with this?
Yeah, so the higher order rewrite rule, that I think you're asking essentially about this subset.
Yeah.
If it can be any subset, so it doesn't have to mention all the variables that you actually apply. So it doesn't have to use them.
Okay.
And in that case, it will essentially just produce a constant function as the result.
Okay.
If you go to your evaluation slide.
Sorry, can you?
So in the evaluation, I guess I was confused. Like,
the setup?
Well, yeah. So you said that that your new Fusion rules actually perform worse than the standard Fusion rules, and I was wondering if you knew sort of what was happening there. Right? Is this a sort of fundamental problem? Is this just a matter of ordering of the rewrites, or?
I think there are quite a lot of factors that play into this. So one is because I only essentially changed a rather small part of GHC. I think that so across GHC and even across Hackage, you often use folds and you expect, or use a right fold and you expect it to fuse properly. While under Stream Fusion, you can actually it's much better to use unfolds to define your functions. So I think there's just a whole lot of functions that didn't optimize properly because of this reason. And secondly, there's also the stream fusion relies much more on call pattern specialization in GHC, which is a particular optimization. And I think the heuristics for applying that are not properly tuned to stream fusion yet. So yeah, I think those are the two main reasons, but I haven't investigated this in detail.